So yeah, I think it's time. So we can start with the today's dot solving session. First of all, let me introduce myself. My name is Vikas Kumar Mishra, and I'm from IIT Patna. I will be your I will be your TA in this particular dot solving session of the nanotechnology science and application. One thing is that since today I'm on a leave, at my home, so there will be some noise problem, But there might be some background noise. But from next week onward, I will be taking session from my lab, so there won't be any issues such like that. Okay, so our session will conduct on every Saturday, 3 to 5 p.m., and we try to solve whatever the doubt you guys are having. The first thing is that what is a need of this particular dot solving session, right? So let's figure out some. Stop presenting. So you guys are able to see my screen, I hope so. So here we can see that our course is there, and where all the links are coming out, all the lectures are coming out to us, and which we can watch. And along with that, there will be one more session will be added over here. One more link will be added over here where our doubt solving session will be recorded and will be there. Now, what is the need of it? And the thing is that we can see that there are the Q&A, and people do ask their doubts and all over here, and we try to answer them. So some few questions which we are not able to answer, let's say over here, we will directly try to communicate one on one with each other. And also one thing is that the videos those are provided to us by the online manner, these are mostly recorded one, right? So there won't be any two-way interaction with the professors. There is only one-way interaction, that is from the professor to us. So in order to interact with the students, what is going on and all, like what kind of doubt they are having, so that one can have a two-way live interaction with each other. This particular doubt solving session has been conducted. Apart from that, okay, I think so. This was the most aim that why we want to conduct the doubt solving session. So that, and also one more thing, that assignment questions and all, if you are facing any problem in solving them, we can discuss those things. The main overall objective is that your doubts should be solved, and the second thing is that you are able to solve the assignments question. If we are facing any problem in those things, we can discuss. Obviously one thing is that I cannot answer the all the assignments question as it is, but we can do some similar type of question and get an idea that what is going on. Okay, so with that, let's get started with our today's session. Okay, so the title name is that nanotechnology, science and its application. Let us see what are the things that has been covered in this particular week. Okay, so these are the on an average majority of the top topic that has been covered. There is a we covered that what is the definition of the nanomaterial in certain extent, like in a broad way also, and we try to understand that okay, how the size is going to affect the properties. In that way, there is also modification in the definition of the nanomaterials. Those type of definition we have considered. Next, we went to the what are the types of nanomaterials, right? That naturally synthesize and those things. And then their synthesis process, top down and bottom up approach. Like there were the two approaches we were having, top down, and then we were having the bottom up approach. What we were trying to do in the top down and bottom up approach, we have understand that in the lecture. If we just like from the for the top down approach, we can say that we are trying to break. Okay. Something is trying to So from the top down approach, what we want on an average Uh, Dear sir, Ramesh, if you are possible, can you mute yourself if there is no question you are having? Yeah, that's great. In the top-down approach, we are trying to break the material and we are trying to convert them into the smaller size. Like we have in the metals, we know that when we roll the material or when we pass them in the through the channel or we do the cold working, okay, those things can decrease the grain size. In the same manner, we can increase the extent to which we are decreasing the grain size and keep on going. We will reach the level where a nanomaterial can be formed. Okay, and this is what the top-down approach is. In the bottom-up approach, it is mostly followed by the nature. Like it will build one atom at a time, and on top of it, one more atom will come and it will deposit. It will form a cluster. We have seen what cluster is 50 and 55 atoms of gold in the perspective of the gold. And those clusters again merge and they form the nanograin or nanomaterial, we can say. In the next lecture, we went through the history of the nanomaterial, that how our evolution might be taking place. Like we've seen the example of the elephant and the deer, why the elephant are quite bigger and why the deers are comparatively shorter than them. It might be the nature that the survival of the fittest is happening, and we have seen from that perspective that how our evolution can. Okay. And there was an interesting talk by the Feynman. We have discussed that part, and there we got to know that how is the Feynman ideology on the nanotechnology, and whether we are able to apply those things over here in our current world or not, and those things we have discussed. Okay, so these are the list of the topic that has been covered in the in this particular week. Okay, so before I proceed to the questions, I would like to ask that is there any doubt you are having from the lectures that we have saw? Those three lectures which we saw in the week one. If there is any, please feel free to unmute yourself and interact with me. And also, you can write in the chat box and we can have an interaction. Okay, since there is no, you can go ahead and try to solve few questions which will be helpful for us to answer the questions of the assignments. Okay. Okay. So let's see here. In this particular question, what we are trying to do, the question is that what is nanotechnology? When we are having the four options with us, we want to know that it can be MCQ, it can be MSQ. So we want to know what can the answer will be. What is a nanotechnology from our perspective, which we have learned in this particular video. The option one is telling that nanotechnology is related with the design and fabrication of the object of 10 to 100 nanometer size. Something around that, okay. If the size of the material is between the 10 to 100 nanometer size, then we will call it to be the nanomaterial, and the technology coming from that, it will be the nanotechnology. Is this particular first option is correct? What we are thinking? In our mind, we can answer ourselves that, okay, it can be true, yeah. Yeah. So Nisa is telling that it is true. Yeah, it's the correct one. Perfect. So we can say from the size perspective that yeah, it is the correct option. So in a broad way, we can say that the first option is the correct option. Let's move to the second one. What about that saying the same thing, but the size this time has been changed? It is from the 100 to 1000 nanometer. Is it a correct option? I, what do you guys say? No, it's not a correct option, obviously. From the size perspective, we see that then it is incorrect. Because usually we thought that, okay, it is from the 10 nanometer to the 100 nanometer. Okay. Now, the next question is stating that the technology relates with material having the noble physical or chemical properties. Uh, from this perspective, we have defined the nanomaterial that it should have a noble physical and chemical properties. See, we can take a material with us. We can take any material. We can modify that material in a certain perspective we either making its grain size to be smaller or making its grain size to be the large. In whatever the aspect, it can change its physical and chemical properties. Nanomaterial is not that something which is related with the change in the physical and chemical property only. Yeah, that's it. So, so we can say that if we see from the definition of the nanomaterial, the third option, that is the nanotechnology related with the material having the novel physical and chemical properties, no, it is not. Option D, yeah. Option D is the correct option essentially. Perfect. So we are dealing with a technology which is related with the physical, having the material properties such that they have the noble properties by the virtue of their size. I should correct this particular statement in a certain way by size in the nano range. Right. So here we can see that in the D option, we are changing our perspective, we are changing the size, and with the change in the size, our physical and properties are getting changes, and it's changing drastically when compared to the micromaterials. Okay, keep on decreasing the size. In the later on stages, we will find that the mechanical properties, like when we decrease the grain size, we know that okay, our dislocation will pile up, strength of the material will goes up. But later on, we will see that if we go to the nano range, it is might possible that we are keep on decreasing the size, but still the strength is not getting up. Instead, it is getting down. We'll see that like this is one of the properties which I am seeing that. Okay. So in upcoming lectures, in upcoming weeks, we will see those things. Okay. So in this particular question, that what is a nanotechnology? In a broad way, one can say that okay, it is related with the size directly, like 10 to 100 nanometer. Or one can also say this is the last one is more appropriate definition to say that okay, the physical properties and the chemical or the properties of the material is going to change when we are moving from the range of the micro to the nano world. Okay, is there any doubt in this particular question one? Please let me know. If not, then we can move ahead to the next question. One more time, I will say that since today I'm on a leave and I'm taking the class from my home, there will be some background noise and all. Next week, from next week onwards, I will take my class from the lab, and those things can be neglected, will be minimized. Since there is no doubt, we can move to the next question. Question number two. Okay, let me say something. Nano represents the size, so answer should be the terms of size only. See, nano is representing the size. Yeah, it should be in the terms of size only. But we cannot directly write that okay, certain range of the number. Like the first definition itself is right, correct. What you are saying from certain perspective is also correct. But the way we are defining the nanomaterial, just because we are keep on decreasing the size, it's not. It should lead to something more in the property point of view. It should some drastic change in the property should occur. One can always say that okay, yeah, I'm having the material with my in my hand, having the size of 20, it is a nanomaterial. But from the application point of view, from the science point of view, nanomaterial has been designed in such a way that it should have a different property compared to the its other form. For example, be it TiO3. In the later on, we'll see that when we are keep on decreasing the size of the material, size of its grain size, its property, optical properties is getting changes. And in the nano range, the property is quite different from that which is in the micro range. So in that perspective, it is correct. So your answer, and that's why we are taking the both of them to be the correct. That is the one and first and the last one. In both of them, we can see the word size is there. So we are not neglecting the size. We are taking into account, but we are also relating with the properties, so that we are like the most important thing for us is the property of the material which is going to affect the application. So from the application point of view, we are sticking with this D option. So both of them are correct. Yeah. Let me know if it's clear. Yeah. Okay then. Since there is no doubt, we can move to the next question. And the question number two is says that what is the biggest problem with a top-down approach? Okay. Uh, First of all, what is top-down approach? We have just now discussed in certain way that let us say we are having a material having the large grain size, some in the micro range. We are deforming it with a deformation. We are making it small, quite small, in the scale of the nano. So, what is the biggest problem in this? Let's see from this all these options. What can be the correct answer? That the increase in the surface area will increase. Yeah, it will increase. There is, but what's the problem in that? It's not a biggest problem, right? If we are decreasing the size, surface area will increase. Increase the internal stress. Yeah, internal stress will also increase. The These two things will occur, right? The option C is the correct option. Perfect. So we can see here that the imperfection in the surface structure will occur. Like we know, if you are taking the FCC, let us say my crystal is of FCC over here, entirely thing is of FCC. But now there is a lot of grain bond is accumulated in this particular nanostrip. Now what will happen? At the surface level, there is a surface level. At the surface, there is a lot of surfaces also, since we are decreasing the size. Okay, so we can see that on an average, if I say that if I keep on decreasing the size, grain size, let us say this is a grain size, and here is overall the volume fraction of grain volume fraction. So the fraction of the atom that is at the surface, that is at the grain boundaries, those things they are getting increases. So if I went to something like let us say 10 nanometer to the grain size, okay, this is 10 nanometer, then something around 30% of the atom are sitting at the surface, and the structure of those will be quite different. So their defects, their imperfection in the surface structure will be very different, and this is the main problem over here. And this can be reduced. This particular thing can be minimized if we follow the bottom up approach, right? This imperfection which is created, it will be minimized. And the option D is reduce the gives the energy. uh, we are deforming it, we are increasing its energy. Overall in the process it is decreasing, but over the energy of the material is keep on increasing, right? So this is also not a perfect answer. A and B is also not a very perfect answer, that okay, it's the biggest problem. The biggest problem is the imperfection that is caused. I couldn't understand this again. Yes, please repeat. See, let's ignore this part. This will come in some later on stage. What I'm trying to say on an average is that if I keep on decreasing the size of the material, the overall atoms that are sitting at the surface, they will try to relax now. Okay, because why they will try to relax? They have the sufficient energy. Now they want to relax in such a way that the energy can be liberated, and that will cause the defects. Okay, and those defects which is accumulated at the surface will result in the imperfections. Okay, and because of that, those imperfections, our material will be like most of the time it is influenced by the defects property, the surface relaxations and all. And that is the imperfections. Defects are the imperfection. There are the more surface, there are the more imperfections, and we want to avoid that, right? So in the larger grains, in the larger grain, we were not having such imperfection with us. Like we were having the surfaces, but those surfaces are quite smaller compared to the over volume of the material. But here in the nanoscale, when we keep on decreasing the size of the material, the this surface are getting the increase. Surface to volume ratio is increasing, right? And that is something which is causing the more of the defect into the material, and that defect is something is imperfection, and that is the biggest problem in the top down approach. Okay, that's great. So if there any is there any doubt in this question number two? If there is any, we can discuss. One more thing I would like to say that you can also unmute yourself and discuss with me if you want to have a direct interaction, and chat is also fine, not a problem. Now, if there is no, let's move to the next question, question number three. Where did I get my paper? Yeah, now let's see the question number three and let's try to answer it. The question is, what is a driving force in the bottom up approach? Okay, so we have to see it from the perspective of the driving force. Why something in the bottom up approach, what is happening first of all, that one atom is coming. Let us say evaporation and condensation type. Okay, where we evaporated it, now it is condensing on a material. So let us say this is our material on which it is condensing. So one atom is coming over here, it got condensed. Another atom again is coming, it got condensed over here, and the so on and so forth process. They are forming the cluster and they are growing. In this entire thing, what is happening? What is the driving force that they are converting into the? They are converting from the bottom approach, the preparation in the nano. Sorry, the preparation of the nanomaterial from the bottom up approach. What is the driving force from? From the top down approach, we know that we are applying the external stresses to it, deformation process. Those things we are applying to it, and that's why it is happening. But in the bottom up approach, why it's happening? The question number, the first option is saying that it is increment in the internal stress of the material. Internal stress of the material is increasing, but is this is a driving force? Increasing the energy is not a driving force, right? Second, reduction is in the grip free energy. Is the reduction in the grip free energy is a driving force over here? Reduction in the surface energy, increase in the surface energy. So on an average, what is happening over here? Reduction in the grip free energy, can it be decrease in the surface energy, increase in the surface energy, and increment in the internal stress of the material? So from your perspective, what are the, yeah, decrease in the surface energy? Yes. So is there any other? Is there anything like? Will there be any conflict over here that something is, there can be other one more option, or this is sufficient, like this is MCQ or MSQ? Since I'm not specifying whether it's MCQ or MCQ, there can be something. See, few people might be thinking that it may be due to the decrease in the gauge energy. It can also be the one of the answer. Like certain extent, yeah, it can be answer. And decrease in the surface energy is also an answer. Increase in the surface energy, it's not happening itself. Increment in the internal stresses of the material, stress increase, if it is increasing, then it's not a driving force itself. It's increasing the energy. So on an average, we can say that yeah, decrease in the surface energy is happening because surfaces are there, they are coming close to each other, and this entire process will happen only when the gift energy is decreasing and the reduction in the gift energy also. So this both of them are the correct answers. I should say is slash R. Okay. So from the top down approach, we got to see that okay, we are providing the externally we are providing the energy to the material. In the bottom up approach, they are condensing in a such a way on the material that their surfaces are now getting eliminated, and that is something which is liberating the energy. Overall energy of this material is decreasing, and it is majorly caused by the surface energy, decreasing the surface energy. Okay, and that is decrease in the surface energy, one of the factor of the Gibbs free energy. Gibbs free energy is overall the general, is a general way. Pardon me. Okay, let me know if there is any doubt in this question number three. If there is no, we can move to the next question.
Could you explain why there's a reduction in Gibbs free energy?
See, surface energy, Gibbs free energy is consisting of the all the energy term with itself, right? Delta G is having volume term also and surface term also, right? So it is also one of the factor. Gibbs free energy is the overall generalized factor, while surface is one of those factors, right? So if surface is decreasing, surface energy is decreasing, in a way we can say that yeah, they are directly proportional with each other. Delta G will also decrease.
Got it. Thank you.
Yeah. Let's move to the next question. Question number four. Uh, let's see this question. What is not the benefit of the bottom up approach? Let's see this from the perspective of the how it is beneficial compared to the top down approach. So we are having the four options with us, and let's try to find out what are the what are the answers. So from your perspective, what can be the correct option in whole? Less crystal defects, homogeneous chemical composition, better sort and long range ordering, less surface energy, which are not the benefits in the bottom up approach. Crystal defects will decrease. Yes, this is the benefit. This is the benefit. Okay. Defects will decrease compared to the top down approach. Homogeneous chemical composition compared to the top down approach, yeah, it will be. This is also the benefit. Better sort and long range order. Is it better sort and long range order? Yeah, this will also be the case because compared to the top down, bottom approach, we are doing it quite slow process. Okay, so the things are that their ordering will occur in a proper manner. They are having one by other. They are forming the cluster, and once they are formed the cluster, they will form the nanomaterial from it. So they are having the quite long range order. Here, less surface energy, which are not the benefit of the bottom up approach. Less surface energy, is it? Is it one of the benefit of the? Both of them are having the lesser. Sorry, less surface energy. It's not possible. Surface energy is increasing, right? So it should increase. This is not the benefit. While in the other way, we can say the crystal defects will be low, homogeneous chemical composition will be there, yes, and better sort and long range order will be there. So A, B, and C, these are all of these are benefits. And if we see from the bottom of approach, surface energy is increasing. No, it's not increasing. Surface energy is overall decreasing. Sorry, surface energy is overall compared to the top down approach. They are same on an average. Okay. So which are not the benefits? We can say that this last one is not the benefit. Remaining thing are the benefits. So if someone want to prepare a homogeneous material, homogeneous nanomaterial, the best option would be to go with the bottom up approach. See, the bottom up approach is not a bulk process. It's not like a bulk way one can do. While the top down approach in the bulk manner in the industrial level can be done. So this approach is quite costly, and that's the one of the reason that it's not use. It's not in much of the use. But if someone is reading the quality instead of the quantity, the bottom up approach is the best approach over here. While in the preparation of the nanomaterial. Okay, so that's how the bottom up approach are beneficial to us. Let's move to the next question. Question number five. Before that, let's go with the other question number 6, and then we will come back to the question number 5. So here are the list of the microscopes are there. Our eye itself is one of the microscope, and on the right side there is a resolution limit. What are the resolution limit of them? So if I match, if say that one is optical microscope, then FESCM is there, and there is a transmission electron microscope, and human eye is there, having the resolution of something A, B, C, and we need to match them. So among this optical microscope, FESCM, TEM, and human eye. Uh, let's start with the human eye. What do you think? The four which match with the which of the particular resolution? Four will match with the B. Perfect. Our eyes is having the resolution of zero point 0.1 mm. Obviously, again, it's from the 1 feet distance. Okay, so zero point 0.1 mm of thickness. Uh, any point, any two objects which are separated by the zero point 0.1 mm, we can obviously see them easily. We can say that yeah, they are the two different objects. But if the distance between them is decreased even further than zero point 0.1 mm, we won't be able to see them. Okay, so with that, 4 is matching with the D. What about optical microscopy? Now we need better microscope to see the things, right? Compared to our human eye. So optical microscope, yeah, it will match with the zero point 0.2 micrometer. Yes, Anisa. So with that we can say that the optical is matching with the option D, zero point 0.2 micrometer. So compared to our eyes, again see these particular values which I am representing over here, they are not the absolute values. There will be some changes because the aberrations and all those things are there. They can cause the resolution of the microscope can be improved and can be decreased also. So, but typical sense, the overall feeling that we want to see that in what range they are lying, some particular value. Okay. So if someone is asking you what is the approximate resolution limit of the resolution power of the resolution limit of the optical microscope, we will say that okay, it's zero point 0.2 micrometer. Our human eyes is 0.1 mm. Okay. So with that, now let's move to the next, that is FESM. Now FESM should have even more better resolution power. So what do you think? Which one FESM will match with? B and D are already over. Sorry, B and D are already over. We are left with A and C. Yes, perfect. Yeah, Arvagami and Ganesha. And say yeah, perfect. It will match. Uh, see, if you are talking about the FESM, they are typically like zero point 0.2 nanometer. We can go. If you want to go to the Armstrong level, we need to use the transmission electron microscopy, having the more energy in it. Okay, so that's why FESM should have the zero point 0.2, approximately zero point 0.2 nanometer. Again, yeah, if someone selling that increase the resolution to a very far extent, I'm correcting all the aberrations you're having, which is typically not possible to remove all the aberrations, all the defects which are uh, optical defects, due to the lenses conversion. There's a lot of stuff going on in the FESM. So on an average, we are saying that yeah, around some nanometer, best to best, we can go. In order to go to the Armstrong level, we have to use a transmission electron microscope, and that's how this entire thing is. They got evolved in particular fashion also, like first our human eye came obviously, then optical microscope, and then SCM came, and then FESCM came, and then TM came. Okay, so in this particular manner the resolution has increased, and also we can see that the since the TM was the one, it's usually most of the time is used to observe the nanomaterials. See, some once I wanted to measure the particle size of the powder which I was having in my lab. I was not knowing what the particular size it was having, because the label on that bottle, no, anything, if I am ordering something from, let us say, Sigma Artist, they will provide the bottle, and on top of it something will be written that okay, this particular size, this is a cache number and all. But that thing got removed. Now I need to find out what is the particle size so that I can use it. I wanted some nanomaterial. I wanted to go to some micromaterial, micro size, 60 micrometer. So I went to the I went to the FASM and I tried to show them that okay, I want to find its size. We are keep on increasing the magnification. We are keep on increasing the magnification. Still, we are not able to recognize it. Later on in the TEM, I got to know that the size is extremely small. Size was something around 1 nanometer, 1 to 5 nanometer is what line. I was not able to see that from the FASM. Again, that's one of the reason that why I'm saying that this is not the absolute value. Your FASM and my FASM can differ. It might be possible that the institute in which you are, your FASM is quite better than mine. So that's how it is. So, but while with the help of the transmission electron microscopy, I was able to recognize okay, this is the particular size of my pod, and that's how it is. Let me know if there is any doubt in it. If there is no, let's go ahead with the question number 5. Here is the question number 5. Here we want to know that by what method surface energy of the nanomaterial cannot be minimized. Like which of this process is not causing the reduction in the surface energy? Is it the surface relaxation? Why surface will relax? That is also one of the question. Second, agglomeration. If two particles are there and if they are agglomerating and forming the bigger particle, is it leading to the minimization of the surface energy? Third, adsorption. One material is there. On top of that, some other particles, some other atoms have got absorbed. Will this decrease the surface energy? Will this decrease the surface energy and surface relaxation like the how can I draw it? Mm, Usually they will differ from their crystal structure. Let us say this was the crystal structure they were having, and later on at the surface level, this atom has got bonded to over here. Surface has relaxed. This atom has moved from its position due to the higher energy at the surface, and somewhere it's lying somewhere over here. Surface had got a little bit relaxed. This bond within the material, and this bond at the surface, they will differ from each other because of the surface relaxation. Okay, this thing is happening. Whether this will decrease the surface energy, whether this will decrease their surface energy, this will decrease. And what about the nucleation? We were having the entirely liquid, let us say. Okay, in that liquid, something got nucleated. If something has got nucleated, what does it mean? That its surface energy, surface, there was no surface in the liquid, right? But here, something has got nucleated. It means that the surface has formed. So it's very obvious. Like I think you got the point, right? You got the answer that this is a something which is going to increase the surface energy. It's not going to decrease the surface energy. The last process. Because if the nucleation will occur, the surface will be created. It will not be like here we can say that the this particular particle and this particular particle, they are coming close with each other, they are adsorbed on top of it, they are decreasing the surface, and so they are decreasing the surface energy. These two particles, they are agglomerating with each other and then forming the bigger particle. Maybe they are not completely attached, but yeah, they are forming some bond with themselves. And this is again, this particular surface has been decreased. Here also, an atom has relaxed. Okay, So now it is not bonded. It is not. It is now bonded with both of the things. Surface has bonded with the multiple of number of atoms having the different bond. Surface has relaxed, and surface relaxation is not leading to the surface energy decrease. Sorry, it is leading to the decrease in the surface energy, while over here the surface energy is increasing. So only the nucleation is there where the surface energy is increasing instead of decreasing. While in the all the process, surface relaxation, agglomeration, and absorption, there is no decrease in surface energy. One more thing that once we these are the some little bit of flavor of what entirely we are going to do in our course. So if few things that are very difficult to digest right now, maybe in the upcoming weeks we will be able to digest it very quickly. Okay. And so with that, this is a question number 5, and we have answered that the nucleation is is a method where the surface energy is not decreasing, while in the other cases, the surface energies are decreasing. If there is any doubt, please let me know. Okay, since there is no, let's move to the next question. Question number 5 is over, question number 6 is over. Let's move to the next question, question number 7. Now we have to write down, this is a very interesting question that we have to write down the size of the earth in the nanometer scale. Let's see. So the size of the this is the diameter I wrote 1 to 12,756 kilometer. Let's convert them, and we need to go to the till the nanometer scale. Kilometer can be converted to the meter by 10 to the power of 3 of meter. Meter can be converted to the millimeter by 10 to the power of 3 again. It will be millimeter. Then we can again further convert it millimeter to the micrometer 10 to the power 3 into 10 to the power 3 into 10 to the power of 3 micrometer. Overall, it is 10 to the power 9 micrometer. It is 10 to the power of 9 micrometer. Now, we can again further convert it to the micrometer to the nanometer. We want 10 to the power 9 micrometer converted to the nanometer. It will be 10 to the power 3 again. So, overall, we can say that it will be 10 to the power of 12 nanometer. Okay, so 1 kilometer is around. So, this much kilometer will be here, it's visible 12,756 into 10 to the power of 12 nanometer. So we can see that we can convert anything to this particular scale of nanometer. Okay, so just converting something to the unit of nanometer, does it make the particles, that particular object, to be the nanomaterial? The unit has not nothing to do with it had something to do with the nanomaterial, the unit. So now our question is that is Earth a nanomaterial? What's your opinion on that? So the again, obviously, the option is no, it's not, because we can see that first of all the size is quite large, and we can convert anything. Like you can convert your height. Okay, you can convert this particular pen which I am holding with me to the nanometer, sorry, nanometer range. But just by converting it, the thing in the nanometer range doesn't confirm that yeah, this is a nanometer. Okay, no, depend on the particle size, not the overall size. Perfect. Yeah, that's very yeah, correct option. So it will depend upon the particle size, not the overall size of the material. So one can convert any unit of the length to the nanometer scale, but it doesn't guarantee that okay, it is nanometer. Okay, now let's discuss one problem where let's see in this particular way that we are having one material where its width is around 10 micrometer, Sorry, its length is around 10 micrometer. Its width is around, let us say, 5 micrometer, and it's having the thickness is around the 50 nanometer. Is this a nanomaterial? So yes or no? Is this a nanomaterial? Having the two dimensions in the micro scale and one dimension in the nanoscale, is this, will we call this particular object, will this call this particular material to be the nanomaterial or not? Okay, so let's say yes, in the broad sense we can call it to be the nanomaterial. Okay, Anisa is telling. Yeah, what about the others? What is your opinion on this? So this is the one case. Let's say take one more case. Yeah, it is a nanomaterial. Yeah, perfect. So Ramesh is also telling that it is a nanomaterial. That's nice. What about this particular thing? Okay, let instead of drawing this, how about I directly write that 10 micrometer, 10 micrometer, and 10 micrometer, 10 micrometer, 10 micrometer, 10 nanometer, 10 micrometer. So we are having the four options: one, two, three, and four. Here, let's say LBH. We can define anything: length, let- let's take thickness. One, two, three, four. Among these four, which are the nanomaterial and which are not the material nanomaterials? What is it? Let's answer that. Which are the material nanomaterials, or which is a nanomaterial? What's your thought on it? Two, three, and four are the nanomaterial. Perfect. So two, three, and four are the nanomaterials since their dimensions is lying in the nanomaterials. Right. If any, so here we can conclude that if any of the dimensions that are lying in the nanometer range, like around 100 nanometer or 10 nanometer, we can call them as a nanometer, even if the one of the dimensions. Despite if other dimensions are larger, it doesn't has to be that okay, all the thing has to be this only, then only it will be correct. Like all of them has to be, all the three dimensions has to be the nanometer range. No. So we can see that we know that there are also something known as nanowire, nanofiber. Their one dimensions are in the micrometer range, while the other two dimensions lies in the nanometer range. They are the nanoplates, where one of the where two of their dimensions are lying in the micrometer range. Yeah, and one of the dimension, that is the thickness part, it is in the nanometer range, and that's how it is. So we can convert anything. So overall, the question was that we can convert two things we have concluded from here, that we can convert all the units of the length to the nanometer, but that doesn't guarantee that your material has to be the nanomaterial itself. We on a broad way we have stick with our range of the nano size, which we discussed. Another aspect is that even if the one of the dimension is lower than the is in the nanoscale range, we will call the material to be the nanomaterial. And with that, we have finished out this question. Question number 7. Okay. Now let's move to the next question, question number 8. So here the question is of the true or false type, like quite childish type, right? In the 10th and 12th we were used to do this. So there are the four. In this particular question, we are having the four question total, and we want to find that the among all these four, which one is true and which one is false. The first thing is that the bacteria is a incidental nanomaterial. Is it true or false? So we are having the total three types of nanomaterial: natural, incidental, and man-made. Yep, perfect. Arivagam. I hope, yeah, I pronounced it right. Okay. So yeah, bacteria is not a incidental nano. Sorry, bacteria is an incidental nanomaterial. No, it's a natural. By natural way, we are able to process it. Though this is a false. Uh, See, there was one bacteria which put lot of lives up and down. Coronavirus, right? Uh, was it a nanomaterial? What do you guys think? Whether it was in the nano range or not? And was it natural or man-made? Okay, I think we can put this on side. For timing, let's only answer that the whether it is nano was in the nano range or was it not. So let me tell you that the on an average the size of the coronavirus was around 150 to 50 nanometer. So we can say that yeah, they are lying somewhere in the range of nanometer to certain extent. So some fraction of them. So most of them are the lying in the nanometer nano range, and we can say that yeah, bacteria. It's one of the bacteria. It's one of the virus, right? So we can say that it is also coming under the nanomaterial range. Nano. No, okay. Let's move to the next question. Nanomaterial incorporate in the skin cream can enter into the human body through the human pores. Is it true? Yeah. Okay. So yeah, it's true. Perfectly right. Yeah, it is true. So what is the size of the human skin? Pore in the human skin. It is around. Yeah, we all know that. Yeah, finish. Uh, I think it was around 50 micrometer. Okay. I think it is somewhere around, yeah, 50 micrometer over. Yeah, that's right. So around 50 micrometer it is. And the nanomaterials are quite smaller than them, right? And that's why we can say that they can, since nanomaterials are smaller dimensions, they can enter into the pore. And this is a true. So we can say that this second option is a true. What about the third one? Cluster have the larger size compared to the nanomaterials. Clusters are having, okay, it's not the cluster, it's a cluster, okay. Yeah, it's false. See what is happening, we are having the atom is getting agglomerated or forming the bond with each other, and they are forming the clusters, and those clusters are again merging with itself themselves, and they are following the nanometer, okay, nanoscale. So approximately we can say one cluster will be having something around 50 atoms. It will again differ from material to material. Okay, some In some it can be 55, it can be 60, 75. But we can say that on an average that the clusters are quite smaller compared to the nanomaterial. So this is a false. So clusters are having smaller size compared to the nanomaterials. Now next, let's go ahead. Let's go ahead. Nature uses the top-down approach. Nature uses the top-down approach. Is it true or false? Yeah. Arivagam, yeah. So it's Arivagam is showing that it's true. What about the others? What do you think? Whether it's a top-down or bottom-up approach, what nature use? See, nature usually it's a bottom-up approach, right? So top-down approach is something which we are using. Like if I want to, just now we in 2 minutes back when we were trying to make a particular this particular size of grain into the smaller grain, what we were doing, we were deforming it. We are making it smaller by the deformation process. We are going from top to bottom. While the nature has a different rule. So nature, even we can see that the ice that are grown, right? They are grown from one small crystal will be nucleated, and on that they will new again will put up and they will grow, start growing. Okay, nature uses the same process. One atom will form, another atom will form, another atom will form, and on top of them, they will keep on growing. So they are starting from the extremely minute particles, atom, and from there they are building up. So from the bottom they are starting, from the atoms they are starting, and they are built, or we can say the atom or molecule, I should say, and they are building their structure in that from that way, and they are converting to the nano, or we can say micro. So nature usually use bottom up approach, and that in that way also it is very like evaporation condensation. It is very we can say that the defect free things are there. While here we are also including lot of defects. So let's not debate. Overall, nature is using the bottom up in broad way. In broad way, we can say that yeah, nature is using the bottom up. So here we can say that this one will be false. This is false. Bacteria, I put three of them to be false. Nature uses the top-down approach. Yeah, it's false. It's true. Cluster have the largest size compared to the nanomaterial. False. Yeah, it is like that. And that's how we solve the question number 8. If there is any doubt in this particular question, please let me know. If not, we can go with the next question, question number 9. Okay, so let's read this further question. Here it's saying that if the size of the human body get doubled, keeping the density to be the constant, then which of the following is slash are true? So what is happening? So we are increasing the size of the. My drawing is very bad. So we are increasing the size. We are making them double. Okay, this is twice. Keeping the density constant. So their densities are equal. Then which of the okay yeah so yeah Anissa is telling me that the option A is the correct option, that overall stress on the leg will increase. So yeah, let's see whether this is correct or not. Let me tell you, yeah, it is correct. Like it's the same type of question which has been solved by a professor in the dot solving, sorry, in the recorded videos. We are taking the same ideology, we are taking following the same path and trying to see that okay whether what are the things that are happening over here. So let us say we are talking about the leg. So leg is getting double over here. So L, B, and H both are getting double. So overall volume, let us say L, B, and H The product of them is over here. Here, the volume will be 2 times of L, 2 times of width, and 2 times of height. So multiplication will give 8 times of L, B, H. Right. Now, let's talk about this particular area, cross-section area. So since we need to talk about the stress that is occurring. So what we want to know that what is the area and what is the weight, what is the force that is applying on that. Okay. So mass we know, density into volume. So overall density is fixed. So the mass is directly proportional to the volume. Since densities are fixed, right? So density is mass upon volume. So we can say that the mass will be product of the density and volume. Since the densities are constant, so we can say that it is only directly proportional to the volume. So now the mass of the final, like M final and M initial. M final is quite higher because its volume is quite higher. Right? Since V final is greater than V initial. And the factor is of 8 times. So M final is something around, it's not something around, 8 times of M initial. So overall, the stress that is occurring onto this particular area, let us say this area. So what is this area? This is breadth into height. This is also breadth into height. But here breadth and height are comparatively different. That is 2 times of breadth and 2 times of height. So overall area is 4 times of BH. Here 1 times of BH. So let's try to calculate the stress on it. Stress in first case, it will be directly proportional to that. Let's incorporate the density also. So overall L B H rho divided by B and H. So overall we are getting L and rho. In the second case, I should follow some proper way of writing. In the second case, the stresses are like volume, that is 8 times of LBH times rho, and we have to divide it by B into H, that is the overall area, that is 2B 2H, and we are getting here it is something around 2 times L and rho. So here we are what we are seeing that the stresses are getting enhanced if we double the size of the human. So if my size get double, so my leg will be facing the more of the stresses. It's more. It will get more heavier. And see, usually I don't know how to what extent it is correct. Like people say that the heights during the ancient time, there is that era, the average human height was quite higher. It might be it has to do with something that okay, and our height is decreasing. It might has to do with this stress part, that things are that with the time is keep on passing, the overall height is decreasing. It can be one of the reason, right? Since the stresses are increasing, so in order to this particular stress to get down, what will happen? The stress can go down if the height get decreased. So from here, if let us say I get shorten up, my leg will feel even less stress, right? If I get more shorter, and that's how it is. So we can say that the overall stresses on the leg will increase. That is the correct answer. Overall stress will decrease. No, this will happen when the size will decrease. Okay. No observation stress change. No, we have seen that the stress change will occur. And none of the work, I just wrote this because I was not getting any other option. Like, how should I make the question? So I made it. So overall, among these three things, we can see that the overall stress will increase if we increase the size of a human, keeping the density of them to be the constant. And with that, we have finished this question number 9. Let me know if there is any doubt in it. Okay, since there is no doubt, let's move to the next question, question number 10. Now we need to classify this particular till these six things, six method in the top down and the bottom up approach. So lithography is there, chemical vapor deposition is there, ball milling is there, salt gel process, equichannel axial pressing, and physical vapor deposition. All these terms, major of them we might have heard, some of them we might have not heard. But still, let's try to see that in what way we can classify them. And if there is any particular thing is needed, I will explain those things. Okay. So let's first discuss about the top down, and then we will discuss about the bottom up. So let's not bother all of them. How about you give me top down approach among this? Like which one of you think that this is a top down approach? Ball milling, yeah. So ball milling we can say it's a top down approach. So here ball milling is there because we are crushing it. So soldier is a top down or bottom approach. Uh, I think yeah, it's bottom. Perfect. So sol gel is coming under the bottom approach. In sol gel is happening that the we are preparing the solution, and in that precipitation is happening. Okay, its liquid is there entirely. In a general way, if we don't know what salt gel is, let's take some little bit of analogy that its liquid is are there, and those liquid are getting precipitate out, having some material in that, and that material are getting precipitate out, and from there, this process we are getting the nanomaterial. Okay, so we are building from the nucleations. We are starting from the, and we are starting with the one atom at a time, right? And so which is a bottom up approach. What else can we think of? What about the physical vapor deposition? Is physical vapor deposition like we are evaporating and then we are depositing on the material on some particular substrate. So is that a top down or what? But see, we have evaporated that, right? So now our chamber is filled with the gases, and now those gases are getting condensed on some cool chiller. It's cooled down. It's like it will be cool. Now one atom will sit at a time and they will start forming the clusters and they will. So we are starting with the, this is our starting point. On an average we can say this is our starting point and we are depositing on it. So all the physical vapor deposition, let me tell you where it is a PVD, PVD, CVD we might have heard. See, whenever someone go, that someone is using the ceramic sample, let us say ceramic material they are having, and they want to do SEM of it. So what is the first thing that operator do? They do the gold coating onto it, right? And that gold coating is what? It's a physical vapor deposition. Having the gold uh, gold substrate at the top, or source of the gold at the top, it is getting evaporated and then it is physically they are getting deposited on the material, and that's how it is a physical vapor deposition. So in that way, we can say that yeah, PVD will be the bottom of approach. So PVD, or yes, chemical vapor deposition is also a bottom of approach. CVD. Okay. Yeah. So we have done with the chemical. We are ball milling is done. Soldier is done. Physical vapor deposition has been done. Lithography. What about the lithography? What we learned, what we understand from the term of lithography. Just the word. What does it mean? Yeah, it's related with the painting. And now I think so related with the painting. Yeah, it is related with the painting. That's right. Yeah, please pardon me for that. See, yeah, we were discussing about the lithography. So we are having some material, we are having some substrate with us. Okay. Now we are applying some paint to it. We are having some material. Now we are applying some paint, some etchant to it. Let us say etchant. We know like what etchant will do. It dissolve out the things that is having the higher stresses in the material, right? The reason which is having the higher stresses. So onto the material, we are depositing the liquid which is treating as a etchant. It's like a painting, na? Just like you have said that we are painting onto it. We are having the material, we are painting onto it, and now the due to the etchant that action, the thing will that it will dissolve some of the material from it. So now initially it was something like this, having something like this. Let us say we are applying the etchant, and let us say there are some stresses over here. We're not need to understand entirely. We will discuss this in the upcoming weeks and all. So we can say that they will remove out some of the materials from the higher stress region and they will form them. So overall, we are starting from the top only, right? We are starting from the bulk. We are applying the agent sum to it, and that is something converted into the lower size. So this will come under the bottom up or top down approach. We are starting with the bulk. We are applying some agent. It's a top down approach. Yes, perfect. So it's a top down approach. So we can say that this is a top down approach. Chemical vapor deposition is a bottom up approach. Ball milling was a top down approach. Salt gel was the bottom up approach. Equichannel uh, angular pressing. Let's discuss about it in the detail. For a timing, let's not bother about this particular E. And the PVD, we got to know that this is the bottom up approach. So, leaving C, we are clear with all the stuff, right? A, B, C, D, and till now it's clear. Okay, so now let's go back to my presentation which I have made. I will stop sharing this. Okay, start presentation. Is my presentation visible to all of you? I think my presentation is not visible. Okay, let me share again. Yeah, I think now it is visible. It's not in the entire full screen mode, but I hope it's fine. Okay, so here, what is in ECAP? What is happening? Equichannel angular pacing is one of the severe plastic deformations. See, I told you that in top-down approach, what we are doing, we are deforming the material. We are having certain material with us, and we are deforming it. So this particular video, I took it from one of the website which is attached over here. You can see what is happening. They are taking the material, they applied some lubricant on top of it. Right. Once it is entirely coated with the lubricant, now they are placing it in a channel, and now from that channel, what they will do, let's see, they post it and they bring it from certain angle. So let's see what is happening, what happened entirely. So we saw this particular video. Stop presentation. Let's go back to our. So there was some channel like this, something over here. They put their material, their straight material like this. They put it and then they press it. So what will happen when it will go through this particular channel? It will sear, it will deform, right? It is going to deform. So if the grain here was like this, after coming from here, where the material was like this grain must have deformed. See, their channels are equal, their size are equal, but they are at the angle. So they are calling at the equal channel, equichannel, angular pressing. It is angular, so and we are pressing it. In short, I usually call it ECAP. So from here we can see that it deformed. Let us say from here it was, let us say the grain size was 100 micrometer, and here we, after deformation, we only got 25 micrometer. Deformation is not completed yet. We are not, yeah, it's top down approach. Yeah, perfectly right. Rivagam. So now see what happened, that 100 micrometer it was there. Now it got converted to 25 micrometer. Now what should we do? We again want to deform it. Put it back at, put this again back on top. We take this material, we got it over here, we got the deformation. It's not deformed yet according to you. If you want to deform more, if you want to decrease the size more, put it back, press it. It will again go away, and next time it might be 10 micrometer or so. So with 2 3 cycles of deformations, one can entirely do this converting micro to the nano. And now, yeah, that's how I want to say that, yeah, since we are converting from the top, like the bulk is there, and from that we are deforming it, we are making it small by the deformation process. You see, this deformation is quite severe. We are doing multiple times, we are deforming the material quite a lot, right? So that's why it come under the severe plastic deformation technique. One of the ECAP is one of the severe plastic deformation techniques. Okay, and that's what it was saying in the presentation. So this is how it was. Now, I hope it is clear. So with that, we can say that this particular will also come under the top-down approach. So we were having a total of three, I think three, one, two, three, yeah, three top-down, and the remaining three, CVD, PVD, and the soldier process, those were the bottom-up approach. These terms we are going to hear multiple times in the upcoming weeks. Maybe not in the second week, not in the third week, maybe fourth and fifth week. We will definitely hear it. If you do any course of the nanomaterial, they will talk about the how the preparation is on an average taking place, and in the in that preparation, these are the most general methods one used. Okay, so with that, all the questions are over. Question number 10s are over. There were, I only prepared the total of 10 questions. I would like to ask you that, is there any doubt till now? Please let me know. Maybe from doubt solving session, or from the whatever the weak content we got from the videos. With that, I hope that we will be able to solve all the assignments question. But before we end, let's see few more couple of slides. I will try to present it to you. Let me stop this. I will share my slides. I hope the presentation is visible. So that's how we have learned that we are we are again refining the green to a very large extent. It is also the one of the, we can say that the code working we are doing onto the material, and also we are not decreasing its cross section area. So again, this video was not taken by me. I not made it. It is by this RSP technology, and the link is given over here at the bottom. Now, few natural thing that is for us, that is a deco, right? We know that it can climb onto the wall, it can climb onto the flat screen, right? Even it can climb onto my laptop screen that with which I am presenting it to you. Why it is happening? So if we see the feet, if we see the feet properly in the SEM microstructure, those smooth, which we are not able to see with our final eyes, that we are seeing that okay, these are the smooth leg and all, but at the micro scale, when we go to the electron microscopy, we can see that at the state that are available to us, which we are able to see. It's like fibers type of stuff are there. If we again magnify this particular fiber, we'll even zoom it, then we'll say that special type of some crystals are available. It's like so it can fix on to any of the surfaces. Like it will be very small. It's in the range of the nano. Okay. Also, we know that why this are they are able to walk onto it. Why they are not falling by the gravity? That is also one of the question which is coming in our mind. So this since these are the hundred and thousands of bristles are available in one spatula. Sorry, in one state. So see how many of billions are there, millions and billions of tiny hairs are there, and those are having this again hundreds of the tiny bristles, special type of shapes. Now they are forming the van der Waals bonds with the surfaces. So these are that they are at the nanoscale, and now there the number are so high, the interactions are so high that it is overcoming the gravitational forces, and that's how we see that okay, is it was it visible, right? Yeah, I think it was visible. So and that's how we can say that okay, when the gigafeet fall attached to any surface, they will form bond with it. Okay, and that will be very strong. So when we are going to the nanoscale, since the numbers are very high, they are going to dominate over the gravitational forces. The nature of the forces are comparatively quite different from those which are in the general life we ourselves are accounting. Okay, so that was all that we can see that there are a lot of the nature stuff are there, which again we are going to discuss in the next upcoming weeks. That's how the nature are evolving, how the nano things are getting playing a role with it. Like in the medicine purpose, we know that we use a lot of nanomaterials nowadays. Okay, see, so one of the great personality which all of us know, especially on the 27th of July, it is one of his death anniversary. We can say that. Can anyone know? Tell that who who is that the great personality we the Indians were having, who died on the 27th of July 2015. Dr. APJ Abdul Kalam. Perfectly, yeah. So, according to him, the nanotechnology is a field of future where the medicine, electronic, and medical science they will play a very wide role in the upcoming futures and all. Okay, and with that, in his remembrance, we can say that yeah, nanomaterials are from his point of view was in the 2015, and right now we are able to say we are able to make the nano robots and all those things. So today is his day, and we are remembering him. That's very good for us to know it, right? Okay, so with that, I think we can end this particular session. If there is any doubt, please let me know. And also, one can post their doubts onto the doubt solving forum, Q&A forum. Okay, so let's see the sorry. Before we end, let's see one of the questions by our fellow member. Okay, let me share the entire screen. The question is that I have a doubt on the particular video. In this particular video, what is a nanoparticle and how they are formed? Okay, so in this particular doubt solving session, we are able to answer this particular doubt that how the particular nanomaterials formation is taking place. It can be done either by the top down approach or it can also be done by the bottom up approach. Okay, and what is the nanoparticles? Those also we have seen it from the perspective of the size. We have also seen that from the perspective of the properties of the material. Okay, so with that we are able to tackle this particular question. I will also write the response in this particular chat. So I would encourage all of you, if you are having any doubt, please post it over here. If you are knowing the answer of any particular questions, you can also post it over here. We can have a discussion to a larger extent, and that's what this is a doubt solving session, and this group is for the discussion of those doubts. Okay, that was all from my side. I think we can stop right now. If there is anything else, please you can mail me back. Bye bye. My PPT. Yeah, yeah. So yeah, one more thing I forget to tell you. This channel which we are having. Okay, Windows. So here, one more thing will be added. One more section will be added of the doubt solving sessions, and in that, if you click on the link, you will be provided with all the what we can say all the PPTs which I make, and also the videos that we have discussed right now. Along with that, we can go to the YouTube channel, my own YouTube channel, and there I will upload lot of stuff. So let me tell you my channel. I will click you the link over here. So previously I was taking the class on the nanomaterials. Sorry, previously I was taking the class in the crystal symmetry and tensor by the Professor Rajesh Prasad. And in this particular channel of mine, we will be able to see that. Along with that, I will create one more playlist over here, which will consist of my PPTs and also this particular interaction which we had just right now. Okay, so please go through it and let me know if anything else is required before we end. Like, okay, that's it. Thank you all.